Hello everyone and welcome to this coffee conversation on the topic of haloacetic acids. I'm pleased to say that today we have my colleague Gemma Ellison, who is an experienced ion chromatography analyst, on the call to introduce us to the topic of haloacetic acids. Hi Gemma, how are you today?
I'm very well, thank you, Simon.
Good to hear that. Well, let's get right into the conversation then. I've heard the term haloacetic acid before, but I have to say I don't really know what these acids are. I don't know much about them. So what actually are haloacetic acids?
Okay, so if we go back to basic chemistry terms, then haloacetic acids, also known as HAAs, are small carboxylic acids where one or more hydrogen is replaced by a halogen. So they are not naturally occurring compounds but are produced as impurities in drinking water after the disinfection process. So for this reason, they are also referred to as disinfection byproducts or simply DBPs because we all love a three-letter acronym.
Okay, thanks for the quick introduction, Gemma. So how many different haloacetic acids are known about?
Okay, so from a regulatory perspective, there are 9 compounds that are considered, and 5 of those, referred to as the HAA5, are of major concern. So are you ready for some more acronyms? These five compounds are monochloroacetic acid, MCAA, dichloroacetic acid, DCAA, trichloroacetic acid, TCAA, monobromoacetic acid, MBAA, and dibromoacetic acid, DBAA. And the remaining 4 primarily identified HAAs are bromochloroacetic acid, bromodichloroacetic acid, and dibromochloroacetic acid. And in addition, there's a 10th HAA, tribromoacetic acid, TBAA, and this can be monitored too, but is currently unregulated.
I see, that's quite a lot of acronyms. So you mentioned that HAAs are drinking water disinfection byproducts. So what particular dangers does water represent that requires it to be disinfected prior to drinking?
Yeah, it's an important question. So as we know, water for drinking starts off its life either in a stream or a reservoir. And however, there's naturally occurring organic material from plants and animals that can wash into the water source. And ultimately, this means bacteria. So to simplify the processing of water, there's generally some filtration that occurs, but there are still organic materials that pass through this process. So the water must also be disinfected before consumption to control the risk of potential waterborne infectious and parasitic pathogens, viruses and fungi. Treating and purifying of water goes back centuries. So it was quickly known by our ancestors that the clear water was generally safer than, say, swamp water. And ancient civilizations were shown to have exposed water to sunlight and also filtering with charcoal. I also found a process where impure water must have been purified by boiling and then dipping a piece of copper in the water 7 times before filtering. So I don't know how scientifically precise the 7 dips of copper were, but ultimately it shows the importance of drinking water to life, no matter what the era was. And perhaps we wouldn't be here if they hadn't have created these early processes.
That's fascinating. There must have been some method development or something behind the decision for the 7
Definitely
dips of copper. That's quite fascinating.
Yeah. But it wasn't really then until the 1800s when there was more understanding about bacteria. And this was mainly due to the large outbreaks of cholera. And there was a famous one in London in 1854. And it was Dr. John Snow discovered that cholera was actually a waterborne disease. And the outbreak was located to a single water pump, which was contaminated with sewage. So very nice. But from that point on, disinfection of water came into the process and has been routinely carried out in Europe since the late 19th, early 20th century. And it's typically a chlorine treatment added to the water as chlorine gas, calcium hypochlorite or sodium hypochlorite. And the disinfection processes now are fairly standard and obviously really well controlled. But you do get variation from country to country in which disinfectant is preferred. These disinfectants are typically free chlorine, chloramines, chlorine dioxide, and ozone. And these compounds are really effective in removing disease-causing microorganisms. But because there's some organic material still present, the disinfectants will react with that material and form these disinfection byproducts. And this table shows the treatment and then the related disinfection byproducts that can occur. And this is where HAAs come from and how they're produced.
I see. There's evidently quite a background to the HAA story then. You mentioned earlier that 5 of the HAAs are of most concern. And why is that? And why do we need to measure HAAs specifically? Are there health concerns, or what's the story behind that?
It's a very good question. So ultimately, water is life. And, we have a fundamental human right to access safe drinking water. And we know this is not a privilege that's afforded to everybody, sadly, but the water disinfection process is a very important step to reduce these preventable diseases. But there are over 600 disinfection byproducts known, and only a handful have really clear data on their risk to health. And HAAs are included in this because they are one of the most abundant disinfection byproducts. Others of concern include trihalomethanes, chlorates, chlorite, and bromate. From the animal studies done on HAAs, the health risks include increased risk of cancer, problems in the central nervous system, liver and kidneys. So, it's really important to measure these, monitor them, and understand them further. The various regulatory bodies around the world have imposed strict maximum concentration limits, as well as unregulated monitoring of other DBPs and emerging DPPs, which include iodine compounds. So it's ultimately a potential health threat that causes the need for measurement and monitoring and to keep gathering that information.
I see. I can see how important it is to quantify these substances then and detect them in drinking water. So thanks a lot for that really interesting introduction to the subject of haloacetic acids, Gemma. It's pretty clear now to us that there's a vital need to measure them in drinking water to ensure that the disinfected water doesn't end up presenting a chemical hazard in place of the microbiological one. So thanks to everyone who's joined our conversation today. Gemma will be joining me again for the next haloacetic acid coffee conversation, in which we will discuss what existing legislation there is for monitoring haloacetic acids in water. Thanks again, Gemma, for your time today, and thanks to all of you for listening. Bye now. See you next time.
Thank you. Bye-bye.